Hi there. This video is intended to explain to learners how they may successfully evidence all 12 assessment criteria for Pearson BTEC, HNC Engineering, Unit 5, Renewable Energy. So what does Pearson expect for learners to go through Unit 5? So Unit 5 is renewable energy. It is a research project. So it's expected it's primarily based on secondary research, as in research that other people have done and published on. However, you could do your own primary research, for example, taking details of a solar panel PV system, data logging and analysing the results. That would be your own primary research. So how are we going to kick off this assignment in terms of providing a professional written report? So what you're going to do is you're going to tackle P1 criteria first. So P1 says create diagrams showing the working principle of most widely used renewable systems. My guidance would be to evidence the working principle of solar panels as in PV, photovoltaic cells, wind turbine, and biomass. And then by choosing those three systems, you can then compare and contrast. Once you've got up to speed with the opening section for the report, you can get into exploring the rates of adoption of renewable energy resources. Personally, I would leave D1 to the end and use that as a final concluding section in your report. So we tackle P1 first, then M1, and then for P2 and M2, describe how renewable energy systems can be of benefit to the local community in terms of developing microgrids, smart grids, provide benefits to the local community in terms of local employment, cheaper electricity, a cleaner environment, and so on. D2 is summarizing the efficiencies. That tends to be more aligned with P1 and M1 once you've differentiated between power, energy, load factor, and so on. And efficiency could be brought into there. And then P3, M3, D3, construction costs of typical renewable systems, compare and contrast against conventional. My guidance would be that that is best analysed and evaluated through a levelised cost of energy. And then finally, PESTEL, looking at different aspects in choosing a particular renewable energy source. It's not just about the money. PESTEL, political, economic, social, technological, and environmental aspects that you need to analyze to go into your decision-making process as to what is the best solution for the particular vocational scenario that's given in the assignment, so that again it enables learners to identify professional context. Again, just to reiterate, using appropriate technical terminology is very important to show professional process, particularly for this research project. We want to differentiate between power, energy, efficiency, quantitative, qualitative, safety, risk assessment, and load factor. And we want to make sure we understand those terms, particularly power, energy, efficiency, and load factor are often quoted in mainstream media, but it's not always obvious whether these terms have been actually used accurately or not. Efficiency is physics related. It's generally speaking material dependent. Power out over power in. For example, a PV panel uses a photoelectric effect, photovoltaic cell. You're taking in sunlight, electromagnetic radiation within that narrow spectrum that we can actually absorb with our eyes. And infrared, it's typically 20% efficient, taking in the electromagnetic radiation and generating DC electricity. Wind, typically 40%, it's limited by there's a BETS limit on it. It's the physical limitations of taking the kinetic energy out of the weather system. Biomass is typically 30% efficient, dictated by the Carnot cycle when you get into the laws of thermodynamics. Load factor LF, efficiency and load factor are independent. Load factor is the number of hours out that you can get the rated power against the number of hours typically it's done over a year. Energy is not the same as power, it's related. Power is the rate of doing work. Energy is power times time. So it's the amount of power over a period of time. If you typically take the meter in a house, 1 kilowatt hour means that, for example, if you had a 1 kilowatt electric oven on for 1 hour, you would use 1 unit of electricity. 1 kilowatt hour is the unit of electrical energy. So load factor is related to energy, not necessarily power. It's because it's over a period of time. So it's how many hours in a year typically you do per annum. Can you get the rated power out against the number of hours in a year? So typically on PV systems in the UK, the load factor would be as low as 10%. So it's weather related. It depends on the weather, the location, the angle of orientation to the sun, and how much maintenance you do. Wind is again weather dependent for load factor. Any corrosion of the blades is going to have an effect, the level of maintenance. Biomass tends to be downtime for refueling, downtime for maintenance, rather than weather dependent in terms of load factor for biomass. For M1, the adoption of renewable, it's likely to be dictated by political and economic drivers such as Net Zero 2050, which is a legal requirement in the UK. Just reiterating, differentiating load factor from efficiency in power and energy. Load factor of PV typically in the UK would be 10%. Load factor in Spain is likely to be double that, simply because they get more hours of sunshine throughout the year. Now, load factor will impact the levelized cost of energy and capex in terms of the payback time. It impacts costs. If you look at other countries like Norway and Paraguay, for example, they use hydro because of their geographical locations. Iceland, geothermal. These are renewable sources, but again, they can do that simply because of the geology and the geography of those particular countries. You can work out rated power by looking at case studies, and you can look at the claimed energy output per annum, and you can work out load factor from this. Both size and efficiency affect power output and obviously energy out of a system. Load factor affects energy out, not the rated power, because it's the amount of time you can run the rated power for. You can do various comparisons. It's interesting to look at published case studies of renewable implementations on, for example, roofs of factories, and by fairly quick analysis and shaking the figures, you can see whether their figures appear to really make sense against what you would expect out. Efficiencies, we're talking about the physics of the system. Efficiency may change with age. Typically, I would recommend doing the cost-benefit analysis through a levelized cost of energy. In terms of my guidance, it would be a 20-year lifespan. At most LCOEs, generally speaking, use 25 or 30 years, which I tend to believe is pushing the limits of really what's achievable. Photovoltaic solar panels, the efficiency does degrade over time. That's a well-known, researched outcome. So that does impact the cost, the levelized cost of a PV installation. So for example, if you start off with 20% efficiency, it could well drop below 18% after 20 years. Now, that doesn't sound like much of a drop, but initially it is only 20%. And you get in, so 20% to start with, 2%, that's a 10% really drop over that 20%, over that 20-year lifespan. Yeah, again, if you look at PV efficiency, if all other variables remain constant, looking at load factor, if the efficiency goes down, then the power output goes down, then the energy over a specified time period must go down, then that will affect the levelized cost of energy. It will affect your cost benefit analysis. Again, we can use the same approach with wind turbines. Wind turbine efficiency will degrade over time. It depends on the maintenance. It depends on the corrosion of the blades. Biomass, we're talking about a combustion engine. I haven't actually specified here any degradation that goes on. Again, it's very impacted, heavily impacted by the quality of the maintenance. For P2 and M2, we're talking about a microgrid. So it's a local grid that actually could be independent from the national grid. Smart grid scaffolds on top by adding digital flexibility. One example of what you could do with your installation is actually overscale the power rating so that any surplus of electricity that's not being used can be sold to the local community, or develop a microgrid, for example, for one industrial estate or one housing estate. And you provide benefits to the community through local jobs, cheaper cost of electricity, and security of supply, which is more of an intangible benefit. For P3, M3, D3, we're asked to do a cost benefit analysis. My guidance would be the best way to do that is to target it through levelized cost of energy. It could also be done through energy return on investment. Yeah, so if you use levelized cost of energy, it's the sum of costs over a lifespan divided by the amount of energy generated over that lifespan. I normally do over 20 years. Some case studies do over 25 to 30 years. To my mind, that's too long a time scale to be really pragmatic in terms of how technology may change and how maintenance may impact. If we look at the final learning outcome, we're talking about PESTEL here. So you need to, as a learner, you need to define PESTEL. So political, economic, social, technological, legal, and environmental. It's a 6-component analysis that is asking you to take a broader view of just the money. So particularly social impacts, environmental impacts may override your decision may override financial considerations dependent on the locality where you want to install renewable energy. There's different techniques for tackling D4, SWOT, questionnaire, and so on. Decision matrix may be the most simplest one. And again, it's about meeting local needs, and it is targeted at environmental analysis as opposed to any other aspect of PESTEL. Again, if you're going to use a decision matrix for D4, KISS, keep it simple. 3 or 4 criteria. You don't need 10 or 12. Keep it simple, but it is targeted at environmental criteria, and take a holistic approach. You can include social cohesion, social feedback in terms of local community needs and the impact on local community, and determining how the local community actually sees or what's their take on environmental impacts in terms of visual and pollution. How does that impact the local community? Wind turbines would be an example. Wind turbines have a massive environmental impact. Noise, visual, so on. My guidance would be for D1 is to use D1 as the final conclusion once you've addressed all other criteria and you're pulling all the analysis together and you're given evaluation. So it's based on facts, it's objective. And you want to take a holistic system view in describing the value of technology that you're going to be an advocate for. But it's all, and through that process of analysis, it's important to consider multiple factors. And again, to show professional practice, good to differentiate between quantitative data shaking numbers and qualitative analysis. They complement each other to get to the roots of issues. You want to be as objective as possible, using logic and reasoning thinking based on evidence. And by doing that, you're going to minimize subjectivity and bias. Thank you for watching this video on Unit 5 Renewable Energy. Please ask any questions or put comments in the box below. And I would hope that that is a broad overview of what is required to hit all the criteria, all 12 criteria for Unit 5. Thank you for watching.